Hello and welcome. This is Roshan, and today we will be discussing one of the applications of the Euler-Lagrange equation. So let us firstly recall that in our previous video we derived the Euler-Lagrange equation from first principles, beginning with a function f of y, y dot, or rather y dash and x. We used a method which belongs to what is known as the calculus of variations, and we found out what this integral is, and we basically minimized this integral. And in minimizing this integral, we arrived at a condition, an equation that looks something like this: dou f by dou y equals d by dx of dou f by dou y dash. And this equation, we called it the Euler-Lagrange equation. So this, you can think of it as a result of our mathematical curiosity, that you can look at it as a purely mathematical setup, where we have this function of y, y dash and x, and in trying to minimize this particular integral, we arrive at a condition, and that equation, we called it the Euler-Lagrange equation. Now, of course, many of you might be wondering, right, what is the use of such an equation? Why did we go through all that to arrive at this equation, and how is this important? Now, there are plenty of applications of this equation, but what we would like to look at in this video is just one of those applications, which sounds silly, in fact, at first glance, but when you try to prove it using mathematics, it may not be so obvious. So here's a problem. We have 2 points, A and B. They're 2 random points, and we would like to know what is the shape of the paths that connects A and B, which would be the shortest paths. In other words, what is the shape of the shortest path connecting A and B? Now you might say that isn't it obvious that it should be a straight line connecting from A to B? And the answer is yes, it is obvious, and we do know that it has to be a straight line, right? It cannot be any other wonky path, or any other random path is not going to be the shorter one. The shortest of all, though you can have multiple paths connecting between A and B, there's only one of those that's going to be the shortest path, and it will be a straight line. Now this is something that is somewhat commonsensical, but let's say we would like to prove it in the spirit of Euclid, the way he goes about doing things in his volumes, Elements, in his very famous books, where you don't take anything for granted, right? You don't make unnecessary assumptions, and you don't rely on just common sense, but you try to prove everything. So let's say if we think in that spirit, how can we prove mathematically that the straight line is indeed the shortest path connecting A and B, these 2 points, or any 2 points for that matter? So let us go about doing that. And it turns out the Euler-Lagrange equation, and in fact our method of from the calculus of variations, is going to be useful in doing this. So let us set up the problem a bit more rigorously. Let us say we have 2 points, A and B, and we'd like to locate where they are. So we use a coordinate system with x and y axes, and let's say A has the coordinates x1, y1, and B has the coordinates x2, y2. And in fact, let's, for the sake of generality, let us not start with the assumption that it has to be a straight line, and let's be open to the possibility that maybe it's going to be a curve, right? A curve connecting from A to B. Maybe that's the shortest paths, and ultimately we have to arrive at the conclusion that it's not going to be a curve, but rather it's going to be a special curve which will be a straight line, right? That's something that we have to arrive at. Now, given this, what is going to be our function? So rather, if you look back at what we had discussed earlier, we have to set up an integral of y dash and x, where integral of a function of y dash and x, and then try to minimize it, right? And in trying to do that, we can use the Euler-Lagrange equation, and then solving that will give us the required solution. So coming back to our setup, the first thing that we're going to do is, let us say that this path that connects A to B has a certain length, right, L, that we would like to know, right? And it is the length of that path, length of the curve, we shall call it, between A and B, is what we would like to minimize, right? So our task is to minimize the length of the curve that connects A and B. And how do we minimize it, right? So firstly, we would like to break this entire path into small lengths, where each length is of magnitude ds, so that you add all these ds's, you're going to get the entire length from A to B. So what would any small patch of this ds look like, right? If you think of it as a tiny displacement, we are going from you're going along the curve, and it's going to be a small displacement. So how can we represent this displacement using the x and y coordinates? So let me zoom in, draw a zoomed in version of that setup. So we have taken a small element ds, and we would like to know how to express this in terms of x and y coordinates. So clearly we can resolve this, and we can think of ds as a displacement of dx along the x-axis and a displacement of dy along the y-axis, so that together dx and dy, if you were to move dx units in the x direction and dy units in the y direction, you end up having made the displacement ds. So therefore, from Pythagoras' theorem, we can write down ds as the square root of dx squared plus dy squared. Right? This is a simple application of Pythagoras theorem, because there's a right angle triangle here, and so these two displacements dx and dy are going to combine in this way to give us the resultant displacement ds, which, remember, is only a small part, a tiny part of the actual path that connects the 2 points A and B. And now, so what is our integral? Therefore, our integral that we would like to minimize should represent the length of this path. So the same length that we had mentioned earlier. So let's call it L, and we would like that. We would like to write that as an integral. So the integral of ds. So I hope you agree that the entire length of the curve between the points A and B can be written in this form. So what we have done basically is broken down the entire curve or the paths connecting A and B into small displacements ds, and then we are adding them up. The integral is nothing but a summation, right, in the limit, and therefore it makes sense to write it in this way, to write that the total length of the path connecting A and B can be looked at as the sum of the small displacements, or you can say the length elements that we have broken the path into. So we are just breaking and adding, right? But then ds, we have just found out, is going to be, can be written in terms of dx and dy in this form. But then let us take dx as a common factor, right? Let's take that out, and we get 1 plus dy squared by dx squared, and all of it is under the integral, and which means I can write this as, and of course all of it is under a square root, and then the dx can be brought outside the square root, and this can be looked at as just 1 plus dy by dx whole square. Okay, so again we should not forget what our aim is. We are just reframing our question here, but what is the original question? It is to minimize this integral, right? We would like to minimize the L. We want, and that's because we want to find out the shortest path connecting A and B. And so our task is to minimize this integral. And in this process, we are basically figuring out what that function is. What is f of y dash x? And it seems like we have almost got it. So we can rewrite this as 1 plus y dash squared dx, where I'm using the familiar notation y dash to represent dy by dx. It's the derivative of y with respect to x. And so now this is our integral. And as you can compare with what we had written earlier, the integral s that we are trying to minimize, when even in the previous video we tried to derive the Euler-Lagrange equation. So this was the equation that we had, the integral that we had back then. And now you can see almost a one-to-one correspondence. The integral s that we tried to minimize there is basically the length L of the curve connecting A and B that we'd like to minimize here. And the function f of y dash x, which is the central thing that you have in the Euler-Lagrange equation, seems to be nothing but this, the square root of 1 plus y dash squared. And so since the Euler-Lagrange equation from this can be written down as we derived in the previous video as dou f by dou y equals d by dx of dou f by dou y dash, we have identified our function y dash x, f of y dash x, as nothing but square root of 1 plus y dash squared. So what remains is to plug in this function into the Euler-Lagrange equation, right? So I hope you remember this was the Euler-Lagrange equation, right? And now we are in a position to use the Euler-Lagrange equation because we know what is f, the function. In this particular case, the function is supposed to be square root of 1 plus y dash squared. So if you plug it into this equation and solve it, and hopefully we are going to get the equation of a straight line, and that way we would have proven that the shortest path between the 2 points A and B is a straight line indeed. So now let's get to work. Let's plug in this function f that we have just found by comparing the integrals that we would like to minimize, and let's plug it into the Euler-Lagrange equation. So let's first things first, right? So let us consider the left hand side of the Euler-Lagrange equation. So as you can observe, the left hand side is dou f by dou y, which means we need to differentiate the function f that we have just discovered with respect to y, which means I need to differentiate root of 1 plus y dash squared with respect to y. Now here you have to pause before you start differentiating, even if you're aware of the rules of differentiation and how to deal with square roots and so on. The first thing you need to notice here is that this is a partial differentiation with respect to y. And if you look at the function is it does not involve y explicitly, right? We don't see y, we see y dash, we don't even see x, right? So though in general the function f must be a function of y dash and x, but like I mentioned in the previous video as well, it need not be, right? Even if it's possible it's just a function of y dash like it is here, which means that when you try to differentiate with respect to y partially, you're treating all the other variables as constants, So therefore this here is basically a constant as far as we are concerned, and whenever you differentiate a constant you end up with 0. So our function does not depend on y explicitly, but we are trying to differentiate with respect to y, so we end up at 0. So the left hand side of the Euler-Lagrange equation is 0, right? Perhaps that makes our calculations simpler, right? So we have discovered what the left hand side is. Now let's move on to the right hand side of the equation. The right hand side of the equation involves, let's first compute the df by dy dash, or rather let us consider the entire right hand side at once, right? So let us compute what this is going to be, and so that once we find that, we can equate it to 0 and get our solution. So let us now consider the right hand side of the equation, which is supposed to be d by dx of dou f by dou y dash. Now there are two derivatives here, right? The first thing we need to observe is, first we are differentiating with respect to y dash, right, the inner part, right? We're differentiating the function f with respect to y dash, and the result of that we are going to differentiate with respect to x. And observe that that is not a partial differentiation, that is a proper derivative, right? And you're going to have to do that in those steps. So do not differentiate with respect to x first, right? So you always go with the inner part first, the inner function, the inner derivative, and then move outwards. So which means we will keep the d by dx as it is, and let us first focus on differentiating the function with respect to y dash, which is 1 plus y dash squared under square root. Right? We need to first perform this differentiation. Now let's recall the methods of differentiation and the formulas. So what is the derivative of this? Here we may have to use something known as the chain rule, and as you may be aware that the derivative of root x is 1 by 2 root x, so this becomes 1 by 2 root of whatever it is, y dash squared, times, using chain rule, we need to differentiate 1 plus y dash squared with respect to y dash, which means 1 becomes 0 and y dash squared becomes 2y dash. Right? So we have performed the inner differentiation with respect to y dash, and this is what we end up with. So let's tidy things up a little. So this now looks like 2y dash divided by 2 root of 1 plus y dash squared. The 2 of course can be cancelled, and now what remains is for us to differentiate this. But before we start differentiating, we need to observe something here. In fact, let us put this back into the Euler-Lagrange equation. So we have the left hand side here. This is the left hand side, and here is the right hand side. And clearly left hand side must be equal to right hand side, right? So basically plugging it back into the Euler-Lagrange equation, let us see what we get, right? So what we're doing is substituting these results in the Euler-Lagrange equation. So let me rewrite the Euler-Lagrange equation just for clarity. What we had is dou f by dou y equals d by dx dou f by dou y dash. So this is our Euler-Lagrange equation. So what's the left hand side? As we found out, it is 0. And what is the right hand side? It is d by dx of y dash by root of 1 plus y dash squared. Now here is the a crucial step. So do not just go about differentiating this, right, and trying to figure out what the derivative is, but instead let's take a step back and think of the very fact that this derivative with respect to x is equal to 0. That's what this equation is telling us, that d by dx of whatever this is 0. What does this tell us about this function that's in the brackets? So the derivative of a constant is always 0, which means whatever is in this brackets must be a constant, must be independent of x, right? So which means what we have in the brackets here is basically a constant with respect to x, right? It does not change with x. it does not depend on x. It certainly depends on y dash, right? And it may depend on y, but it certainly does not depend on x. It does not it in fact does not contain x explicitly as well, and that also makes it obvious. But the important thing is it's a constant, which means writing just what's there in those brackets, y dash by root of 1 plus y dash squared. And since I know it's a constant, let's call that constant c, right? So where c is a constant, right? We are using a symbol to represent the constant, and we get an equation that looks like this. Now let us simplify this a bit so that we can understand this better. And in fact, if you remember, solving the Euler-Lagrange equation means to find out, in this case, find out y. What is y as a function of x, right? So here we have an equation in terms of y dash, the derivative of y, but we'd like to know what is y of x. So this is therefore basically a differential equation that needs to be solved. So for that, let us do first a little bit of rearrangement. Let us cross multiply, and then to get rid of this square root, let us square on both sides. Squaring on both sides, you end up with y dash squared equals c squared plus 1 plus y dash squared. Let's open the brackets, c squared plus c squared y dash squared. Let's gather the y dash squared terms on one side of the equation so that we can pull y dash squared out common, leaving us with 1 minus c squared, and that in turn leads us to c squared by 1 minus c squared. Now remember that c is a constant, right? That's how we had defined it. That's why we introduced it. And now we have such an expression of c, right? C squared divided by 1 minus c squared is going to be a constant ultimately. At the end of the day, whatever this is, right, as fancy as it looks, is going to be a constant, some constant. Of course, not the same constant c, but some combination of c's in this way is going to lead you to some number, some other number, but which ultimately is going to be a constant. So let me call that constant something else. Let's say we call it k. Or in fact, we can do something better. We can even get rid of the square root. Let us do that. Let us rewrite this as y dash, which is going to be the square root of all of this. And now the square root of all of that combination of c's is ultimately going to be a constant, which means I can simply write it as some constant k, right? So let's say it is a constant k, and so what I'm doing is replacing k with replacing root of c squared by 1 minus c squared with k. Now this looks like a very, very simple differential equation, right? Recalling that y dash is nothing but dy by dx, right? And rewriting it by cross multiplying. And now to find out what is y, all we have to do is integrate. So integrating this equation, we get y on the left hand side, and on the right hand side the k can be kept out, and you integrate dx, you end up with x, and of course there should be some constant of integration. Right. Now what is this? Right? So what we have arrived at is the solution, and the solution seems to be nothing but a linear equation. So we can clearly identify that this is a linear equation of two variables, right? Y and x, whereas everything else is a constant. K is a constant, and we have one more constant of integration. But what do linear equations represent? They represent a straight line. So what we have basically is this here is the equation of a straight line. And there's our solution. There's the answer to our question. Our question was, what is the shape of the shortest path connecting 2 points? And we knew that it's going to be a straight line, but now we have proven it. We have arrived at the equation of a straight line, showing that indeed the shortest path between any 2 points is a straight line, right? Is going to be the straight path connecting one point to the other. And so We have done this using the Euler-Lagrange equation and the methods of calculus of variations that we had used in the previous video to derive the Euler-Lagrange equation. So, wasn't this fun? We have basically proved, right, using very rigorous mathematics, something that is almost obvious, and we have had fun along the way, and most importantly, we have learned one application of the Euler-Lagrange equation, one place where you can put it to use and it does give you something that you know is obviously correct. It's more like a verification of the Euler-Lagrange equation than the verification of our common sense notion that it should be a straight line that connects 2 points, that should be the shortest the path between any 2 points. So what we have done today is this: we have used the Euler-Lagrange equation and the calculus of variations and shown that the shortest straight line, the shortest path connecting 2 points is a straight line. So that's it for today. In the next video, we will look at more applications of the Euler-Lagrange equation and which many times defy common sense. So now that we have established our trust in this equation, we will go on to use it in places where the solution may not be obvious, not as obvious as it was here. And that will reveal something profound, something that we didn't know earlier or couldn't have known easily. So we have basically mastered a technique which will keep being useful again and again, and that's what we will dive into in the next video. So until the next video, stay curious, never hesitate to pause and think, sometimes even about the most obvious things that are around you. Thank you.